Hello, everyone. Good morning here in the US. Good evening over there in Europe and in Asia. Greetings to the physics world. I'm so excited about this historical 2020 APS April meeting. My name is Tao Han from the University of Pittsburgh. I'm the chair for the program committee. On behalf of the program committee, I would like to welcome everybody to 2020 APS April meeting. I would have liked to say welcome to Washington, D.C. as my background showed, but unfortunately, that could not happen because of the current circumstances. Indeed, the pandemic has not only changed our meeting plan, but also our lives in many ways. But I wish you all to stay healthy. But science does not stop. Physics does not stop. We are now here at the April meeting that clearly demonstrate our dedication to physics, to science. On the positive side, the current situation offers us new opportunities. We are setting a record to hold such a large meeting online with more than 5,000 attendees from all over the world, even without the hassle for travel. So we have attracted many, many more participants than that in an in-person meeting. For that, I would like to thank you all for attending this meeting. But foremost, I would like to thank our APS staff members for their heroic efforts in such a short time and to have made this virtual meeting a reality. I would also like to thank our APS leadership. Without their determination, their leadership, their strong support and encouragement to the program committee, this April meeting would not have taken place. The theme for this year's April meeting, 2020 Vision, Frontiers in Physics, properly reflects the exciting program here. There will be 3 plenary sessions today, Monday, and Tuesday morning, a public lecture this evening, and 17 invited live sessions, and 100 contributed live sessions from 20 APS units, with a lot of exciting, interesting new physics results. I hope that you all find this meeting inspiring and productive. So before we start our academic program, I want to remind everybody that the April virtual meeting also follows the code of conduct of APS meetings that can be seen on the APS website and in other files. Now let's get started our opening session. The Kavli Foundation Keynote plenary session, Exploring the Cosmos. This session consists of 3 talks by 2 Nobel laureates, Professors James Peebles and Michael Mayor, and by 2001 Nobel laureates in physics, Eric Cornell. The first talk will be given by Professor James Peebles. Professor Jim Peebles is Albert Einstein Professor of Science, Emeritus at Princeton University. He shared the 2019 Nobel Prize in Physics for his theoretical discoveries in physical cosmology. Please join me in congratulating Jim for such great honor. The title of his talk is Exploring the Universe. Now, James, please. I would like to remind you all, please mute your system, and you can offer your questions by typing in the chat window.
Thank you, Tao. Colleagues, I must address you from afar as nature once again demonstrates its power over us. Nature also instructs. I intend to remark on how that instruction went in the development of physical cosmology. I remember as a graduate student being fascinated by a talk by Professor Piet van de Kamp, Swarthmore University, on the search for planets around nearby stars. They looked for the wobble and the position of the star as the planet moved around the star. They used a refractor telescope with an immensely long focal length. It made a magnificent enlargement of the star image, but of course the image by seeing is a blob. They didn't have the technology. Michel Mayor and Didier Queloz had the technology to build the experiment that detected planets. It will be relevant for my concluding thoughts to remark that astronomers estimate there are at least as many planets around stars as there are stars. Our Milky Way galaxy has some thousands of millions of stars like the sun. It's an excellent bet that on all those planets, all sorts of marvelous things are happening that we, the human race, will never observe. I also remember as a graduate student learning about cosmology, I was not so interested. It seemed to me that they had just made up those steady state and Big Bang cosmologies. I learned that that's not quite the whole story when Bob Dickey, who was my advisor as a graduate student and who then became my professor of continuing education, decided that an elegant universe might be one that started expanding in a very hot, dense state filled with thermal radiation. The universe expands, the radiation is expanded and cooled, but it remains thermal and it doesn't go away. There's no place for it to go in a homogeneous universe. Bob invited, I've never before written a talk, but for this purpose, I think I have to, and now I have to read it. Bob suggested that two of his young people, Peter Roll and David Wilkinson, build a microwave radiometer to look for this radiation. And he casually said to me, why don't you think about the theoretical implications? That could be the implication of discovering the radiation or of not finding it. We knew perfectly well that there might be nothing there to detect, but we were young. The projects required interesting theoretical and experimental methods. I expected we'd spend maybe almost a year on this project and then move on to something else. That didn't happen because the radiation was detected. The first slide shows a photograph. Am I showing a first slide? Here, late 1970s, David Wilkinson on the left, Bob Dickey on the right, and me behind an instrument Dave Wilkinson had built with his students that was very important to the development of physical cosmology. It was to be lifted by a balloon above most of the disturbing atmosphere. The two horns at 90 degrees, there are two pairs of horns, two different wavelengths. The radiometer connecting the two horns is very sensitive to differences of flux density coming into the two horns. So as the balloon rotated, the horns scanned the sky and were sensitive to picking up very small variations in microwave background temperature around the sky. So that was an important part of the development of the standard LambdaCDM cosmology. I would remark that the name LambdaCDM has two parts: CDM, a hypothetical non-baryonic, initially cold dark matter, and lambda, Einstein's cosmological constant. Ironic that both parts of the name are speculative, each introduced for the purpose of making the theory fit the observations. Am I still there? I proposed the CDM part in 1982. It was known then that the sea of thermal radiation is far smoother than the distribution of matter in galaxies and groups and clusters of galaxies. Why the big difference? You would have thought that in the early universe, when things were hot and the baryons ionized, the drag of plasma on radiation would either prevent clustering of matter from forming or else drag matter with it as clustering formed and seriously distort the radiation. The way around that, I suggested, is to postulate a new component of matter, cold dark matter, that doesn't interact with matter or radiation. So the structure can start to form in this cold dark matter while not disturbing much of the radiation. I proposed adding the other hypothetical component, lambda, 2 years later. At that time, I had been developing statistical measures of the mean mass density, and I had the wonderful opportunity of joining Mark Davis in the analysis of his first redshift survey that is reasonably close to complete. Mark had been a graduate student at Princeton, had worked with me. He knew full well the value of a complete redshift survey. The results displeased me, I must say, because they said the expansion of the universe is more rapid than escape velocity. Expansion at escape velocity is elegant, we used to say, because it means that whenever we happen to flourish and take an interest in the expansion rate, it will be at escape velocity. That's comforting somehow. I used to like the idea, but it's wrong. In the early 1980s, when I introduced CDM, there was the idea of a cosmic inflation. Inflation, it was said in those days, would iron out all wrinkles, giving us a homogeneous universe. And in the process, of course, it would iron out space curvature. That meant a strong condition on the mass density, or if you are willing to do it, the mass density plus a cosmological constant. At the time, everybody knew that the cosmological constant has an absurd value in quantum physics. But, well, let's add it. And indeed, it proved out to work. I must say that in the 80s and early 90s, the CDM concept was much more popular than I ever thought sensible. After all, it had not taken me much time to put together the pieces for the CDM model. My unhappiness with the popularity of CDM, I'd put it together out of pieces I already had. I could put together other models that fit equally well. I did do that. Why in the world was it so popular? I think it was pure simplicity. After all, you just had to take standard ideas and add one new hypothesis, non-baryonic dark matter. And particle physicists, as it happened, were independently discussing notions of a fourth class of neutrinos that would have a mass around 3 GeV. Those neutrinos would be thermally produced in the very early universe. They would annihilate before decoupling of radiation and neutrinos because they're so massive. And if the parameters are just right, the residual number of these massive neutrinos might be just enough to produce escape velocity. That happens if the fourth class has the standard V minus A interaction, and if the neutrino mass is about 3 GeV. After that notion of non-baryonic matter, there were other ideas floating around. So it was natural enough for me to latch onto that notion. There was another key hint in the late 1970s that the astronomers' problem with subluminal matter. Much of the mass, it seemed, is too faint to be detected. I don't think the people exploring the notion of non-baryonic matter knew about that, or at least knew in any of the details. I was fortunate to know it because I discussed it at length in my first book on cosmology, physical cosmology. So again, it was natural for me to postulate that the astronomer's subluminal matter is the particle physicist's non-baryonic matter. So there was another consideration for the popularity of this model, I think of a sociological nature, we might say. If most of the mass of the universe is in particles that interact only with gravity, then you can set up a pretty good numerical simulation of the evolution of the distribution of mass in the expanding universe and the formation of galaxies and the like by simply following the motion of particles that interact only with gravity. That's easy to set up on a computer. It's hard to do the n-squared operation to compute the acceleration, but you can work on that. So indeed, one of the great attractions of CDM is the simplicity of its simulating structure formation. So in the years around 1990, there was a fascination with CDM, and there were problems with preliminary indications from measurements in progress. for example, to measure the mean mass density, to detect departures from exact isotropy of the sea of thermal radiation, to understand timescales. By the mid-1990s, that had led us to a variety of inventive models: warm dark matter, mixed dark matter, tilted dark matter, decaying dark matter, tau dark matter, tau CDM, LambdaCDM. The thinking was remarkably inventive. Yet I'm surprised to consider very few people strayed from the central notion of CDM. I tried straying. I gave that up with the first detection of thermal radiation anisotropy that proved to look pretty much like what you'd expect in a CDM model. Now, one variant, LambdaCDM, passes an abundance of tests. So was it pure good luck that the community, by and large, stuck to this core idea? I guess so, but we see also the operation of an implicit philosophy adopted by the community. We might as well stick to CDM until we find that it really won't work, or else maybe some variant of it does work. So that was sensible, far better than everyone pursuing his or her own idea, and it was lucky. Let us look now at an example of the test that so impressed me. The figure that I hope will now appear, it does, shows power spectra of the distributions of galaxies on the left and microwave background radiation on the right. Recall that a power spectrum on the left is the square of the Fourier transform of the galaxy positions. There are three panels showing different redshifts, different ranges of redshift. You recall that an expansion factor by 1 plus z is a redshift z. On the right, the analog of a power spectrum for distribution on the sky, the square of the spherical harmonic expansion of the temperature as a function of position across the sky. These two theories have solid lines, which you can barely make out in the right-hand part, that have essentially the same parameters. It's the theory. Impressive to see how consistent they are, deeply impressive to me to consider that on the left, we're looking at the relatively nearby universe. On the right, we're sampling what happened back at redshift 1000 when plasma and radiation decoupled. Prior to that, we recall matter and baryonic radiation acted as an ideal fluid. The electrons scattering the radiation, the ions Coulomb scattering the electrons. It's a fluid with viscosity due to motions of the photons. The oscillations are the result of acoustic oscillations of the plasma radiation fluid. The oscillations rather abruptly stop at a redshift of 1000 when the temperature is dropped to 3000 Kelvin, and the baryons rather promptly combine to neutral atoms. That sets a boundary condition that sets the favored wavelengths that gives us these oscillations. Impressive to see how well this works. But what really grabs me, as I say, is that we're looking at the universe in two very different ways, sensitive to two different epochs in evolution and getting consistency. The next slide shows an example of how that works. Great. I remind you of the way these arguments go. Consider that the cosmic abundance of deuterium is measurable. That's because the Lyman alpha resonance is slightly different because of the different masses of proton and a deuteron. Given the abundance of deuterium relative to hydrogen, and the fact that deuterium doesn't tend to be produced in stars, we have the abundance of deuterium that had to be produced at redshift 10 to the 9th when the universe was hot enough to promote thermonuclear reactions. Given the abundance of deuterium relative to protons, we can infer the abundance of baryons required to produce that abundance of deuterium, and the abundance of helium. Given the abundance of helium and baryons during the oscillation, the acoustic oscillation phase, you have the velocity of sound that affects where those bumps are to be seen in the power spectra of galaxies and radiation. And so one has another constraint on helium. So you look at the right-hand column, helium abundance 0.23 at a redshift of less than 0.1 by observations of plasma around old stars and their emission lines. At redshift 10 to the third, 0.33 due to the wavelengths of acoustic oscillations, and at redshift 10 to the ninth, from what's needed to produce the deuterium, 0.25. These are not precision measurements. They scatter by tens of percent, but deeply impressive to me. They're probing the universe in three very different directions and sensitive to three very different epochs in the evolution of the universe. That's really impressive. You could look over other of these tests, and I'll remark on still another one. Among them, an apparent discrepancy of 10% in the length scale set two ways by measurements of galaxy distances in the universe as it is about now, and what is required to fit what happened at redshift 1000. Maybe that is a result of a systematic error in really difficult astronomical observations. Or maybe, just possibly, it's showing us that the LambdaCDM theory has to be adjusted. I see in the community torn opinions. Many say, oh, the test the LambdaCDM theory passes so well surely mean that it's the right theory and this can't be an anomaly, it must be a systematic error. Some of those same people, of course, are hoping that it's real, because if it's real, it's a hint to a better theory than LambdaCDM. I should emphasize that I'm not arguing that LambdaCDM is to be abandoned. I'm saying I made it of the simplest pieces I could get away with. It wouldn't be at all surprising to find that some of those pieces have to be improved, adjusted, corrected. That would be a fascinating thing, a better cosmology. Now I must offer a brief commercial interruption. Next month, my book, Cosmology Century, will be published by Princeton University Press. The press was going to have a booth at the meeting. They would sell book plates that I would be willing to sign, and that book plate would entitle you to receive the copy of the book next month. You could stick the book plate in it and have my signature. I'm not sure how attractive that is, but in any case, we had to abandon it. Nature will have its way, but the book will appear next month, and it's not very expensive. Okay, I've been asked whether I feel frustrated, maybe even uneasy about the lack of detection of the dominant component of the dark matter. I'm certainly not uneasy. I think the tests we have now are so abundant, so well cross-checked, that the case for LambdaCDM is about as good as it gets in natural science. I, with many others, am waiting with bated breath for news of detection of more components of the dark matter. Meanwhile, there are other ways to examine cosmology for clues to new physics. I'm particularly fascinated these days by theories of the formation of galaxies. Impressive to see how well these very complex computations to simulate structure formation can produce galaxies that look a lot like real ones. Great progress. But details really bother me. And maybe it's wishful thinking, but I'm fascinated with the possibility that we'll learn from galaxies how to get a still better cosmology. Others, great groups, are working hard to see whether Einstein's lambda, not a constant, but rather varying with time. If it varies, it would be wonderful news, because it would mean lambda is not some really odd cosmic parameter, cosmic constant, but rather a dynamical object whose physics is to be discovered, a great opportunity. And then there are those brave souls who seek to tell us how the universe behaved before it was the Big Bang. I offer a last thought. We can only probe those aspects of nature that circumstances allow. I mentioned the enormous number of planets, the fascinating things that must be happening on them that we, the human race, will never see. That's frustrating. Maybe the non-baryonic dark matter in its largest components will never be detected. That would be frustrating too. But let us celebrate how deeply we have been able to probe the nature of the world on a vast range of scales, and how much more there is still left to explore. Thank you. Has that message?
Thank you very much, Jim. Thank you very much, Jim, for this very interesting and inspiring and entertaining talk. So we have some time for some questions. Anyone can type in your questions on the chat window. Please also include your name and institution. Since I haven't seen any, let me ask you, Jim, for one question here. As you said, this inflation seemed to be a very important concept and possible important process in our real universe development. Is any smoking gun signatures that we can rely on? But of course, we know many possible measurements, but I mean whether some smoking gun signature that we can tell this scenario apart from other alternatives.
I have to be impressed by the fact that already in the 1980s, inflation had led people to expect that space sections are flat, ironed out by the exponential expansion, near exponential during inflation. That idea proved to be accurate. Space sections are very close to flat. That's impressive. It is frustrating that we do not have a specific theory of inflation. Instead, the idea is elegant, but a framework for a theory. It makes it difficult to imagine tests. There was great excitement over the possible detection of gravitational waves produced during inflation. That would have been a beautiful clue. It hasn't happened. At the moment, I think it's proper to bear some skepticism toward the notion of inflation because we don't yet have it well tested. My colleague Paul Steinhardt likes to look for alternative models. I think that's very valuable. We must do, but and again, his ideas must be held as speculative until we have more evidence. I emphasize that by saying brave souls enter those waters.
I would like to have two more questions to ask Jim. Jim, could you unmute yourself to discuss these two questions?
Yeah, I've unmuted.
So Jim.
I've unmuted Jim.
Jim,
Yep.
yeah. The first question is from Ganesh Rajaman, Institute for Plasma Research in India. The question is, are there remnants of early plasma embedded in the form in LambdaCDM model, which could be worked out via computer simulations?
Not that we know of. There, of course, the intergalactic medium now is polarized, but the evidence is pretty good that there was a period, say from redshift 30 back to 3000 to 1000, in which the free electron density was quite low, as if the plasma had almost completely recombined. Galaxies, of course, are remnants of inhomogeneities in the plasma distribution.
Okay, thank you, Jim. The next question is from Ken Lu. The question is, why were you disappointed with these simulations of the tails on the galaxies?
Perhaps it's an emotional thing. I'm impressed by how well the images match real galaxies, but I'm also fascinated by the fact that reproducibly over quite a few years, the star populations in simulated galaxies have much hotter orbits, much bigger bulges, if possibly much more random motions within the disks than are observed in nearby galaxies. The galaxies nearby can be observed in the best detail. We should pay a lot of attention to them. And a lot of them are nearly pure disks, very little evidence of a concentration of mass to the center that is so reproducibly present in simulations of galaxies. Maybe that's an artifact of the problems with complexity, or maybe it's a hint to a better theory.